Professor.
Good afternoon, ladies and gentlemen. I'm very happy to talk a little bit about DC technology and power electronics solutions, primarily in the medium voltage distribution level. The previous speaker talked about high voltage DC transmission. But we think that also in the distribution level, DC technology will find its way for a more efficient electrical energy system. So I would like to take the opportunity to quickly introduce our research in Aachen at our university, and then take a quick look what has been achieved in Germany. You know, Germany was one of the first countries to start the energy transition to a CO2 neutral society. And I can tell you already the road has not been so easy. And then I'll look a little bit in what are the technical requirements that we need in the distribution level as far as energy storage and flexible meshed grids like in HVDC are needed. At the end, I already heard this morning that there were several questions about cost, and we have collected some numbers on the cost of these new flexible distribution systems. Very briefly, our university is the largest technical university in Germany, one of the largest in Europe. The interesting thing is that we have 45,000 students, but almost 60% are engineering students. So we are a true technical university. I'm also director of what we call the University Research Campus clusters. A cluster is a collection of research centers. And I'm leading the cluster of sustainable energy. Why did we do this? We found out that engineering studies have specialized heavily, and in order to solve global problems like the energy supply or water needs, we need to work cross-disciplinary across different faculties. And so we started building also a new campus where we have buildings where companies can rent space. So these are buildings built by private investors, and this is the E.ON Energy Research Center, of which I'm director, and in this plot of land we will build a new center for aging and reliability of batteries and power electronics. So at this moment the cluster has three major centers: the E.ON Energy Research Center, the Center of Research Campus Flexible Electrical Networks, where 21 companies are member, and a new center which will be constructed by the end of this year for aging reliability of batteries and power electronics. We also have a very nice center for wind drives. Here you see the Center for Wind Drives, where we can test up to 4 megawatt nacelle to analyze and study the mechanical but also the electrical impact during fault right-through capability and so on. One nice feature is that we not only can connect the wind turbine to an AC grid, collector grid, but also to a DC grid for future collector systems. So we can avoid in large wind farms the expensive converter substations, because each wind turbine already has an inverter which we can use. This is the new center. It will be an investment on research on material science for the reliability improvement and diagnostics of batteries, electrochemical and power electronic systems. You have seen also in the logo of the summit today, in all the applications, photovoltaic, wind, electric vehicles, grids of the future, computer data centers, your computer, your cell phone, everything needs power electronics. We need to convert electricity to the right form for the application. And that means actually that the classical AC grid is not necessarily the right solution for the future. At the E.ON Center, we work interdisciplinary with four institutes on the urban efficiency. So we focus a lot on energy efficiency in buildings, as well as heat storage and also reuse of low temperature heat systems. These are the main research topics. I go very quickly. So we work on grids and storage, buildings and city quarters, digital energy. There will be also a new Fraunhofer Institute starting very soon together, and then also the economical aspects and the user aspects, because we see a lot of rebound effects. When we make, for instance, lighting with LEDs, far less energy consumption, what we found out is that people are installing more LEDs. So the energy savings did not come out as expected in some areas. One complete new center is the Research Center for Flexible Electrical Grids, and this is to accelerate innovation. This is a new vehicle of the German federal government, Ministry of Education and Science, to bring industry and university together, like Silicon Valley, but here we are talking energy. And we work here with many partners, sorry, I'm pushing the right button here, with many partners to develop DC distribution grid and automation in low and medium voltage. As you can see, there are several Japanese companies, Mitsubishi, Hitachi, Fuji, Murata are members of this consortium, as well as big companies like General Electric, Siemens, and so on. One name you won't see here is ABB, but we understand that the previous question, whether Japan is on the same level as the European companies in development of high voltage DC, my answer is Hitachi is going to buy ABB in that sector, so you will have the same level of research. So we are working here on the grid planning, the grid components, power electronic systems, circuit breakers, hybrid breakers, digitalization, but also on the societal economical aspect. And we are also working in CGRE. In C631 is a new committee to provide standardization for medium voltage DC systems, MultiTerminal DC systems. One of the projects that I'd like to conclude the introduction is that we are building between the Center for Wind Drives and our 5 megawatt converter test facility. We have just finished building a 5,000 volt medium voltage DC interconnect, which is multi-terminal. We are connecting 2 substations, AC substations, together, so we can move electricity between the substations and avoid high peak power loading of the transformers. And this is also a demonstration of the technology. One thing I like to point out here is that this is a 2.3 MVA transformer, 2,300 kVA, and it's about this size. Why? Because we are working at 1 kilohertz and not at 50 or 60 hertz. The higher the frequency, the smaller the magnetic components. And this is my main motivation to go to DC technology, is to reduce the consumption of materials. Because we have learned that when Africa and India would have the same electrical infrastructure as Japan or Europe and the United States, there's not enough copper on this planet. So we need to find solutions that we use less materials, which also have an ecological impact, in order to provide electricity for everyone. And I think that is one of the main goals. So the German government, the first thing that always happens is, of course, with all the academies of science, like Ecotech and so on, we made a big detailed study, and a working group was set up. Actually, the working group is led by my colleague, Professor Sauer, who is leading at my Institute of Battery Research. And the leading questions are, how can we transform the energy supply, meeting the climate goals that the German federal government has set? There have been many experts discussing this, and 300 experts have 2 years ago published a paper, Energy Systems, and some of the conclusions I will use in my presentation here. One thing that also came out of the study is that in the beginning, and as you can see, the federal government by 2020 wants to have a 40% reduction of CO2 emissions compared to the emissions of 1990. Now, the European Commission says by 2020, 20%. But Germany, of course, is going to do twice as good. At the same time, we are going to shut down by then the nuclear power stations, which of course do not produce CO2 emissions. So the challenge is quite big. And in the beginning, we were on the good track, but you can see that since the global economic stagnation in 2010 till this year, you can see that actually nothing has been done. The CO2 emissions have remained more or less constant. That means to meet the targets of the federal governments, which in Germany have been put in law, so we have to reach them, and otherwise there will be maybe penalties, that we have to accelerate the reduction of CO2 emissions. And by 2050, there is a debate whether we go to -80 or -95. So the two main reasons that have been identified why we are not, why we are slowing down, that has to do with the fact that we have little progress in energy savings and energy efficiency. And that has to do with the fact that the production capacities have been reduced. So the CO2 certificates have been dropped to 4 euro per ton. Now they have increased again to 24, 25 euros per ton CO2. So now companies are forced to invest in reduction of CO2. But during the global economical crisis, there was no incentives to, let's say, reduce CO2 emissions, because in Europe we could buy very easily CO2 certificates from Russia. They were dumping them on the market because the Russian economy was all the way down. So now the European Commission is not giving as many CO2 certificates as in the previous years, and the price is already going up. Also, we found out that, and as you know, actually the best thing that could happen for electric mobility is the diesel scandal that hit German car manufacturers very bad, so that now we see an increased production of different models coming to the market. But I have to say, to be really honest, that German OEMs for car manufacturers have tried as long as they could not to produce electric cars. We have to admit that. So these are the conclusions of the study, and these are the same conclusions that we drew about 15 years ago when we started the E.ON Energy Research Center. So ultimately, the vast majority of electricity production will come from renewables like wind and photovoltaic, because in Europe we don't have a whole lot of hydropower. Also, we should use effectively biomass, because biomass is also an energy storage, and there has been a lot of debate that biomass is in competition with agricultural land, but there is a lot of waste, of biomass waste, that we can use to produce heat and electricity. Another important thing is what we call sector coupling. That means we need storage, that's clear, a lot of storage, but the storage does not have to be all in batteries or hydro pump power station. Heat storage is the cheapest storage, and we need heating and cooling in buildings, massive, more than electricity actually. So we are looking to all kinds of storage systems, including, of course, ultimately the hydrogen production, so power to X, to create synthetic fuels for those applications which cannot be easily electrified. My institute is now doing a lot of research, not anymore on electric vehicles, but more and more on electric airplanes. And of course, in those cases, you realize that batteries alone will not be able to allow us to fly more than 200-300 kilometers. So this is the challenge. So having these things in mind, we can take a look at what we need, what are the requirements that we actually need from an electrical viewpoint when everything gets electrified. And the first thing that I like to share with you is a bird's eye view. If we can distribute the electrical energy like on a copper plate in the medium and low voltage grid, when we have solved that, then you can make calculations that Mr. Hoffman has done many years ago, that when you have 180% installed capacity of wind and photovoltaic, then you only need less than 2%, actually this is about 1.5% of energy storage. 2% is 2 weeks per year. Now in Europe, we have every 4 or 5 years, in the winter time, when there is very little sun, for 2 weeks, no wind. Very bad air quality. And that means we need strategic storage for at least 2 to 3 weeks of energy. And that can only be done, in my opinion, of course, with chemical energy, hydrogen, that then is converted again to heat and electricity. So for the storage systems, we are looking at fast storage systems, that minutes to hours of batteries for primary energy control, but also dual use of batteries of electric vehicles. This is how e-mobility as a sector can be supporting the electricity sector. This is what we call sector coupling. Large storage systems, seasonal, can be heat. For instance, our E.ON Energy Research Center is heated and cooled with heat pumps, and we have 40 boreholes, 100 meters in the ground, where we store the heat in the summertime and use it back in the wintertime. The cost of heating and cooling the building for 7,000 square meters is very, very low. It's about less than 10% of the cost of a normal building. And then, of course, the strategic storage is chemical energy storage, hydrogen. The studies in Germany show that when we have 80% of all electricity produced by renewables, electrolysis becomes a real business case, because there will be many weeks where we have too much wind and photovoltaic so that we can get electricity for free, almost. I like to point out for the batteries that we have a project with NEDO, one of the companies that you're from Tokyo University, a spin-off, is testing next to my office. Actually, I see this from my window, a container with what I call a hydrogen battery. And you can see the nice thing about this technology, it has a very low energy content but very high peak powers, and it can take many, many cycles. And this is kind of in between a battery and a fuel cell system. But the hydrogen is generated back when we recharge the system. So we are investigating the use of this system as primary energy control on our grid, and later on we will connect it to our DC grid. At the same time, we think it is a good technology for peak shaving, spinning reserve, backup power for fast charging stations of electric vehicles in weak grids. So I did in 2011 a prediction with linear extrapolation based on the installed capacities of renewables in Europe between the year 2000 and 2010. In 2000, we started the market liberalization. And I came to the conclusion that in 15 years' time, by 2025, we could have had a system that all electricity production could have come from renewables, together with biomass and CHP systems that connect the electrical grid, high voltage, distribution and low voltage, to the heat local grids. So we will have more and more in Europe local heat distribution grids. And when we have biomass as well as electrolyzers, we also produce gas, which we can push into the existing infrastructure to distribute gas across Europe and provide the long-term storage that we need. The numbers that you see here are just linear extrapolation, and I came to the conclusion that in 15 years we could have reached it. But then in 2010 came the economic slowdown, and actually nothing has happened. So we have lost 10 years. So I think we will reach that in Europe by 2035, maybe 2040. Now, what does it mean for an electrical engineer, for the electrical grid? And this is very important, and this is sometimes overlooked by many designers of grid designers. 1/3 of the electricity production will be far distance offshore wind farms, hydropower, because in Switzerland and Norway we have a lot of hydropower, will be far distance, but only 1/3 of the installed capacity will be there. 1/3 will be onshore, and combined heat and power in factories or substations dispersed across cities for local heat distribution and CHP, combined heat and power. And 1/3 will be actually in the low voltage, because everyone is installing photovoltaic systems on their rooftops. Plus, we should not forget that when charges of batteries are bidirectional, and now we are looking into bidirectional charges to extend the lifetime of batteries, that actually a huge amount of power capacity is in the low voltage. And how do we deal with that? And in my opinion, the only way to do that is that the distribution grid, like the transmission grid, has to be interconnected. We need what we call cellular interconnected distribution grids. The interesting thing is that in Germany, already 1/3 of the green renewable power is in the far distance high voltage. 1/3, actually more than 1/3, is feeding into the medium voltage at this moment. And almost 1/3 is in the low voltage. So this rule, 1/3, 1/3, 1/3, which I predicted at an APRI summit in Pisa in Italy for the first time in 2012, is actually already happening in Germany. And now the next question comes, what if all the e-mobility goes electrical? How much peak power do we need to install? And the numbers vary, if you manage it properly, from 11 gigawatt to 1,800 gigawatt, which is impossible, of course. And that would happen if everyone starts charging at the same time. So that is, of course, not realistic. But actually, if we manage electric vehicles properly, we only need about 19% in Germany more capacity in the distribution grid than what is today. Now, we can only achieve these systems when we also, in a smart way, distribute the photovoltaic and wind energy. Investors like to install all the wind in the North Sea here and all the photovoltaic here in the south, because that's where they get most return on their investment. But when you do that, we have calculated you need 20 gigawatts of transmission power from the north to the south in the winter time and from in the summer back to the north. And that doesn't make sense. The transmission lines in Germany typically have a transmission capability of 2 gigawatts. So we will have to build many, many transmission lines, and the population does not accept that. It took 25 years to install the southwest line that is now under construction to get permission, and it had to be by law by the government. So what you see here is a total area of photovoltaic that we need in Germany for all the electricity consumption in 1 year in Germany. It's not so big. It's not small, but it's not. And this is the total area for all wind turbines that you would need onshore for all the electricity consumption in Germany. That means we have 200% installed capacity. And if we distribute that across the country, then we can balance solar and wind power so that the storage that we need locally is only 2%. That is the previous graph that I gave you. So the local distribution grid should be interconnected so that we do not have to push the energy from one city to the transmission grid to take it back on the other side of the city. And this is why we look to the DSOs, the distribution system operators, to interconnect their systems, their substations more and more to get the grid more flexible and local. So what are the technologies that we use for that? And especially also like to point out that German car manufacturers are now telling their potential electric vehicle customers that electric vehicles should be charged with 150 or 300 kilowatt. Otherwise, you should not buy an electric vehicle. Of course, that is not reality, but we had 6 years ago, we developed a prototype for the Audi e-tron. This is the car that we developed at my institute. 2 motors in the rear, 1 in the front, and at that time we aimed at a charging peak power of 75 kilowatt. This car is now being produced in the Audi factory in Brussels. Actually, there's a lot of car manufacturing in a small country like Brussels, like Belgium, and it's a very nice car, but they wanted to charge it with a total power of 150 kilowatts. Here you see the platform, and this is why the battery had to be redesigned, not for high energy, but for high peak power. So the range of this car is only 400 kilometers and not 500. Now let's say that you live in Aachen, and a typical substation in Aachen from 20 kilovolt to 400 volt low voltage is feeding, for instance, branches of 21 households, 34, 10 households. The transformers are typically 250 kVA. Now, if you have 6 cars charging at home with 40 kilowatt only, the transformer is totally overloaded. So we have to find solutions how we can bring this high peak power to the users. And for that, we have to take a quick look into how the distribution grid is built. Some of you may know that the distribution grid is radial. That means not interconnected. Now, some people say, yes, but we have these loops here, but these are open connectors. Why do we have them? We have them basically for redundancy. If, for instance, on the left-hand side, the transformer has a problem, overheated, or a cable is disconnected, then we close this connection. This is called a transfer switch. We open this one, we close this one. And that means if the loads are equal, this transformer has to provide now full power. So if you look at all the transformers in the distribution grid, they're never used more than 50% of their installed capacity. We have, for the AC grid, to make it reliable and also to protect faults, the transformers have to limit short-circuit currents. We have overinvested a lot of materials in the distribution grid. And now the question is, how can we use that? And if we make what we call an underlay, not an overlay supergrid, but an underlay distribution grid with DC, we can connect the substations at low and medium voltage with a DC medium voltage connection. And now I can use the remaining power that is available of the transformers to charge these cars, or move electricity from photovoltaic from this house and sell it to these houses. Of course, we need blockchain to balance and do the billing. And so the DC grid allows us to exchange the energy between different substations. And this, in my opinion, this hybrid grid is the first step to DC distribution grids. And ultimately, we will eliminate the AC grid. One nice thing is that you need only DC to DC converters, which are highly efficient and well-developed technologies. At the same time, with power electronic building blocks, we built this redundant so that if one fails, you still can operate with the other building blocks. And this is what we do as power electronic engineers, to have resiliency, to have reliability. And DC is much better than underground cables. So the underground cables is also against earthquakes, against disasters, against flooding, a much better solution. And as I mentioned, you can reroute the energy between that. Now, one thing that also we have found out is that for DSOs, sometimes this is from one company, but the transmission is the TSO, another company. So if you have, for instance, a lot of photovoltaic here, at this moment they have to sell it to the TSO and buy it back in their own grid. To the TSO you pay on average about 4 cents per kilowatt hour of energy. And meanwhile, you're overloading maybe the high voltage grid, which is transmitting the bulk power from big power stations. So if you can do it in your own grid, then you basically save a lot of money. So the DSO is also very interested in that. The technology is there. Here you see our 7 megawatt DC to DC converter, or solid state transformer, working at 1 kilohertz, self-switched. It is a topology that I proposed 30 years ago for NASA space station. So this is space technology, you could say, but for terrestrial applications. So each transformer is about 2.3 MVA, and the efficiency that we achieve is 99% from 5,000 volt DC to 5,000 volt DC. So we think that in the future, in the urban environment, in order to have higher peak capacities, that we will have maybe 5,000 volt DC, maybe plus minus 5,000 volt DC distribution, very thin wires. To go to each home, you will have your solid state, very high frequency transformer, possibly using silicon carbide devices. We can also do it with silicon, but silicon carbide would be very useful on this side to produce plus minus 380 volt, which is compatible today with photovoltaic inverters. So we can produce in Europe 400 volt AC, three-phase 400 volt line to line. At the same time, all the equipment that is fixed, washing machines, heaters, heat pumps, air conditioning, as well as cooking plates and so on, and the charger of the car can be always fixed wire to the DC. And the photovoltaic inverter that people already have installed can be used for local AC production. So we turn it upside down. And that would be more efficient. Now, a last few slides about cost. We all know that the cost of batteries has gone down much faster than we anticipated. This was our prediction. This was the Fraunhofer prediction in 2010. And actually, this is the current price that you have for batteries in automotive applications. The cost of power electronics, and this is where in HVDC, you saw that the previous speaker, Mr. Kato, said the substation, the transformer station is very expensive. But these are numbers of 2014. Meanwhile, the cost of power electronics has collapsed dramatically because of the fact that we have installed by 2017 810 gigavolt ampere. Giga is 10 to the power of 9 of power electronic converters for wind turbines. And therefore, the cost of medium voltage converters has gone down of 500 euros per kVA down to 20. And actually this year, I can get prices of 12. So the converter station has to come down in price dramatically. And why do we believe that? Simply, silicon, PV, you see the prices of PV according to Bloomberg, is made of sand and energy. The energy comes from PV. And the power electronics is used to convert the PV energy into the grid or in applications. And that means that power electronics is made of silicon, that this is a loop, that the price of power converters goes down almost the same like PV. Ultimately, we will only use PV power. Even wind turbines are already more expensive than PV at this moment. And if you look at the automotive, the price of a power inverter will go down to $3.3 per kVA. So a DC to DC converter, which uses both, will go down to about 7 euros per kilowatt. And that is, of course, tremendously cheap and changes the whole perspective of how we can design urban grids and distribution grids. My main motivation, and these are my last slides, is we do it, of course, for efficiency gains. A DC to DC converter is about 1 to 2% more efficient than an inverter connected to the grid with filters and so on. But we can save a lot of material. This is a 50 hertz transformer, 2.5 kilogram per kVA. Our transformer is about 250 grams per kVA, 10 times lighter, 10 times less materials, much, in principle, 10 times cheaper for the same insulation class. And if you look at a typical energy transmission from a power station all the way to the end consumer, in Europe, we use 20,000 tons of copper and steel for 1 gigawatt. So if we make this all 1 kilohertz with DC, then we only use 2,000 tons of copper and steel. We can recycle all the steel and copper to build energy systems in India and Africa. And I think that is the way of the future. And we also did ecological studies. This is my last slide, actually. where we look at all the aspects, toxicity, radiation, and so on, for a 50 kilowatt DC charging station versus an AC 22 kilowatt charging. And you can see that we have on the ecological footprint more than 20% reduction on ecological footprint. So basically, to conclude, the grid of the future will be interconnected with different sectors. So the electricity grid will be connected with the heat and cold distribution, with the gas sector, with the e-mobility sector, also heating and cooling through heat pumps, and of course the cloud will provide the communication, information, and data analysis systems to automate that, because these systems are very complex. At our university, we have positioned ourselves to cover in the cluster sustainable energy all these topics in different ways. And last but not least, I'd like to draw your attention to a workshop organized by the IEEE Power Electronics and Power and Energy Society. It's a fairly new workshop, Electronic Grid. We like to bring the utility companies, the power engineering people, and the power electronics people together, because we have lived too long in two different worlds. And please consider Aachen. Aachen is a nice old town at the border of the Netherlands, Belgium, and the most western town of Germany, and where we can also see our facilities. I hope you have some time next year in November to join us. Thank you very much for your attention.
Professor Doncker, thank you very much. Now we would like to have Q&A session at this juncture. We have question from the audience. HVDC, MVDC, LVDC. In what area would you focus on for your research activities? In which of the three areas are you going to focus?
So, in which area are we going to focus our DC technology? Actually, 6 years ago, when we started with the Research Campus Center, Flexible Electrical Networks, we felt that we had to focus our research on the medium voltage DC distribution. Why? Because high voltage DC voltage source or current source is already well developed. Also, there are only like 4 or 5 companies in the world that can realize that technology. But we also look at the interface of high voltage DC to medium voltage and medium voltage to low voltage. Why is that? It would not make sense to, for instance, take from the North Sea all the wind energy to the south and then distribute it back into the AC grid. We need also high voltage to medium voltage DC substations. And we have developed also a lot of technology with DC converters, solid-state transformers, to go from high voltage at even only 10 megawatts, in which case out of 500,000 volt, you only need a few amperes to extract the power locally. So we can have a multi-terminal high voltage DC grid. So our research is focusing on the medium voltage, but we also look at the interface of high voltage and low voltage.
Thank you very much. We have one more question. In Europe, I think you have various collaboration projects. In the area of DC, what sort of project or collaboration projects are happening in Europe?
Well, in Europe, there are, at the European level, there are a lot of projects going on, like Reserve. Actually, our university is also involved in that. And this is to investigate the offshore DC transmission systems. But the German federal government has basically also provided support for our research campus. They support us with 2 million per year for 15 years on research. When we have also industry partners like Mitsubishi, Hitachi, Fuji, and so on, working with us. They have to put in kind also 2 million per year. And I think we have been quite successful in driving this technology. Of course, there is also a lot of investment ongoing for the automation of grids, for circuit breakers and so on. And last year, the federal government in Germany had a surplus of 58 billion euros. People pay too much tax, I guess. And 15 billion euros will be invested in what I call living labs for a CO2 neutral urban society. So the living labs will be reconverting cities where now they have brown coal and lignite production to convert them completely to renewables and also make people aware of these technologies and get experience. And that will be invested in the next, I think, 10 years.
ありがとうございました。
Thank you very much.
どうもありがとうございました。